Yeah, so the first talk in in the session will be Ulf Leonhardt, who will be talking today about Casimir cosmology. And please take it away, Ulf.
Yeah, so thank you very much for inviting me to speak here, and I also thank the audience for listening to me, even from in such a relatively unusual way. And so this conference is in memory of Renaud Parentany, and I remembered that I met him almost exactly 20 years ago on Capri when we started discussing. This was at the time when there were real conferences, not virtual ones. And we discussed a lot in the breaks of that workshop. And I learned from him the foundations of the theory of Hawking radiation, about quantum physics of the horizon. And he was really the first one from the community with who could explain this to me very clearly. And I benefited over the years very much, especially from his clarity and his way of explaining things, and benefited in my own research. And what you will hear today is also partly influenced by the results of his teachings, and therefore I'm very grateful to him, and he will be definitely remembered. So the subject of this talk is Casimir cosmology. I'm at the Weizmann Institute of Science. And what I would like to talk about is essentially one of the goals of analog gravity is actually to understand something better about gravity. So can we use the insight that we have from other systems, so be it fluid mechanics, with Einstein condensates, optics, and other things, can we use the insight we have from that in order to shed light on some aspects of gravity or astrophysics that are poorly understood? And one of those aspects is what has been known as dark energy, or more prosaically, the cosmological constant. And there's clear evidence for this thing. So this evidence comes from the analysis of how the universe has expanded over the past, and there have been a series of observations. So beginning with the exploration of supernova explosions, then the analysis of the cosmic microwave fluctuations, and more recently, direct measurements of the Hubble constants using bright stars. And the evidence is overwhelming. So there is an additional repulsive force to gravity that acts primarily on cosmological scales, and we don't know what it is. And what I would like to do in this talk is to make a case, and not just a case, but to also be quantitative, that this dark energy could be one aspect of forces of the quantum vacuum that people are familiar with in other scenarios, in particular in atomic, molecular, and optical physics. Now, why vacuum? So why is the quantum vacuum an issue in astrophysics? And the answer is that space is to an extremely good approximation in a vacuum. So this picture that you see here on the screen, this was the last picture taken by Voyager. And you see with, if you're really lucky, and I don't see this actually, oh no, here it is. You see this is the pale blue dot of the Earth. This is everything we have as seen from space. The beams you see in these pictures, they're just reflections of light, and they're not real. And so this is a vivid illustration how empty and how lonely space is. Now, to be quantitative, the figure worth remembering is that the average mass density of the universe is in the order of 10 to the minus 29 grams per cubic centimeters. So it's to an extremely good approximation of vacuum, and therefore the physics of the vacuum applies. And it has been applied. So more than 50 years ago, Zel'dovich, he was the first to formulate a theory that predicted the cosmological constant, so a repulsive source of gravity in addition to the usual attractive ones. And he predicted that from properties of the quantum vacuum. So he got the right structure, the right quantity for it. But he didn't get the right numbers. So if you put in modern numbers into his expression, you get something that is wrong by 120 orders of magnitudes. And so by many, many orders of magnitude, depending on where you put your cutoff. And so this is an issue that standard quantum field theory is not able to explain. On the other hand, we really do have good evidence for actual forces of the quantum vacuum. And this evidence comes without exception from atomic, molecular, and optical physics. And it is related to forces like the van der Waals forces or the Casimir forces. These are the forces between neutral atoms or molecules. And if you put many of those molecules together to form macroscopic objects, then these are the forces between those macroscopic objects that are mediated by quantum fluctuations. And this field has been around for a considerable time, since Casimir's first work from 1948, but it is really in the last 3 decades that, or a little more than 2 decades, that we have entered an era of high precision experiments. So the first one is this paper here from 1997 by Lamarot on precise measurements of the Casimir force. And their recent papers related to our ability to precisely measure those forces and to manipulate them and to understand them, so that there is a very well established experimental technique and also theoretical understanding of such forces. Now, what makes it possible to apply this knowledge that comes from atomic, molecular, and optical physics in astrophysics is an analogy. So this is the theme of this conference, and it's an optical analogy that says that the expansion of the universe, the fact that lengths, the distances grow by a factor that is homogeneous but time dependent, this can be understood as if you would fill the universe with a refractive index distribution, or with a constant refractive index that, however, changes in time. And so illustrated by these 2 pictures. On the left-hand side, you see a cartoon picture of the expanding universe as a function of time. On the right-hand side, you see the equivalence of that as how the refractive index of the universe changes, and the different shades of gray that you see there. Now, this analogy then allows us to apply the theory of those vacuum fluctuations. This theory was developed in the 1950s and formulated in around 1960 in its precise form by the Landau Lifshitz school, and by Lifshitz himself, and by the best PhD students at the time of the Landau Institutes, and as were Peter-Jewski and Dzierżynski in particular. And they developed a theory that agrees very well with experiment. Now, what this theory and also other types of theory have in common is that they require what is known as renormalization. So if you calculate the vacuum energy as it is, the bare vacuum energy, then you get a number that is infinitely large. It doesn't make sense in practice. So what you do is you compare the vacuum energy at a finite distance, for example, a finite distance of 2 dielectric objects that are interacting with each other using vacuum fluctuations. If you compare this vacuum energy at finite distance with the same arrangement of objects, but taken an infinite distance apart, then you get a difference, and that difference turns out to be finite. And this is the one that actually does then mechanical work. However, this works very well in AMO physics, but in gravity, we are supposed to put in Einstein's equations everything there is on energy and momentum in the energy momentum tensor. So all energy should gravitate, not only the part of energy that can do mechanical work, but also this bare energy should contribute to gravity. And yet we have this evidence from cosmology, or I mean, the evidence is overwhelming. So if this bare energy would really be able to gravitate, it would significantly affect everything we have. And so we could view this simply as an empirical fact that says that the bare vacuum does not cause any gravity. There's no gravity from the bare vacuum. Now, because of the other points of view, that the bare vacuum also doesn't do any mechanical work, we could even go one step further and say that there is no evidence for the bare vacuum, no empirical evidence whatsoever. Neither does it do mechanical work nor gravitate. So we should not take it into account. And we should also, in astrophysics and cosmology, we should also use the renormalized quantum vacuum and work with it. And then all you have to do to apply these concepts that are coming from AMO physics in cosmology is to turn this scenario from space into time. So instead of considering a material that varies that has a refractive index distribution that varies in space, we have a refractive index distribution that varies in time, and that will lead to an effective vacuum energy, and this vacuum energy will have consequences in terms of forces. And but there's one caveat, and this, an important caveat, is that the evolution of the universe of course occurs in a continuous way. So it is not as you would have in space. You have one block of material, then another block of material, and they are separated by interfaces. Here you have a gradual transition from one refractive index to the other, and dealing with this problem is difficult. So this has taken about a decade of work and several PhD students, master students, and a postdoc to begin to understand what you need to do in order to apply the Lifshitz theory to scenarios like this of a continuously changing refractive index distribution. And but then you could ask yourself, so okay, even before you do this amount of work, how is it possible? How can the Casimir force, now the renormalized Casimir force, how can it have any effect in cosmology? So Casimir forces are acting usually on the nanoscale. So these are the forces with which, as shown in these pictures, geckos can climb up walls because they have many little hairs in their feet, and hairs stick to the walls, and of forces that are acting on the size of a hair. And so how is this possible that this force plays a role in cosmology? What is, despite the similarities, what is the difference between the Casimir force that we have encountered in AMO physics and the Casimir force that might play a role in cosmology? And the difference is this. The difference is the equivalence principle. So yes, space-time acts like a material, like a medium, but it is a very unusual material. It is the same for everything. So as historically was first shown by the falling tower, supposedly falling tower experiments, everything falls the same way under gravity, everything behaves the same way under gravity, and that includes also radiation. It includes electromagnetic wave across the whole spectrum, whereas ordinary material have a finite window over which they act. And this spectrum is enormous. So it is not just what is shown in this picture, it ranges on a logarithmic scale all the way from the cosmic horizon to the Planck scale. It's an enormous amount of orders of magnitude that are available. So if you have in these materials effects that are sensitive to the entire spectrum, that are sensitive in particular where the cutoff of that spectrum is, where your material then becomes transparent or merges with the background, then if you have a scenario like this, then this may become strong in astrophysics, and in fact it does. So this is
There's 5 more minutes, Ulf.
5 minutes, exactly. That's perfectly fine. So this is what I showed in this paper. And let me try not to go through the technical details of this paper, but to show you what the consequences are and how it behaves, and how it behaves in cosmology. So the cosmic evolution is determined by the Friedmann equations. So the Friedmann equation relate the Hubble constant. Hubble constant is the logarithmic derivative of the expansion factor, relates this to the mass density via Newton's constant. And this is the first Friedmann equation. And then there is a second Friedmann equation that then relates changes in the energy to the pressure. And this second Friedmann equation essentially is just a consequence of thermodynamics, saying that the entropy is conserved. And then the first law of thermodynamics gives you exactly this relationship between energy and pressure. So these are the two basic laws that in an homogeneous isotropic universe, here also assuming without curvature, as we know from astrophysics, that's approximately true, that governs the cosmic evolution. How does this get then, and so this then specifically for the universe we live in is then characterized by what you see here, 3 terms. So the first term relates to the effect of radiation that goes with 1 over the 4th power of the expansion factor. Then this is the matter energy that goes with the cubic power. So matter is just diluted by the expansion. And then there is a term that is constant in the standard model of cosmology. So how does this get modified in this theory of Lifshitz applied to cosmology by an equation of motion? So instead of having a constant lambda, this lambda varies, and the variation of that lambda is related to how the expansion factor or how the Hubble constant has changed over time. And here it is the third derivative of the inverse Hubble constant that determines this. And the coupling factor that you have is given by the effective cutoff and the number of fields involved, and the order of magnitude for this is around 10 to the minus 2. Now, and then it's interesting what happens during cosmic evolution. There are various phases. So we start from the hot Big Bang, which was dominated by the radiation, followed by matter-dominated phase, and then we have the vacuum-dominated phase. And these phases are characterized by these relationship between the inverse Hubble constant and time. So it's always linear. So the radiation-dominated is 1/2 of the time, matter-dominated 2/3 of the time, then vacuum-dominated would be a constant, Hubble constant. And you see that if you plug this into this change of the effective cosmological constant, you see that in each of those periods, there's no change. So lambda or omega lambda can only change in the transition periods. So in the transition from the radiation to the matter-dominated, from the matter-dominated to the vacuum-dominated, and we happen to live just in such a transition period. So we are in the middle of going from matter to vacuum dominated. And therefore, what we should expect is a change in the cosmological constant. And in fact, this has been observed in astrophysics. And relatively recently, there's a series of papers on this observation. This is the latest one with the highest accuracy so far. And so by directly measuring the Hubble constant, there is evidence for this variation of the cosmological constant. The variation is in the order of 10%, and the accuracy of the measurement has reached 1%. And the Hubble constant, as determined from the cosmic microwave background, is also in that with that accuracy. And there is a clear case of a variation of the cosmological constant. And the question then, that's the question that we are working on, is whether this can be reconciled with this theory. So whether the Lifshitz theory of the cosmological constant is able to explain such an effect. And it has already the right order of magnitude. So in contrast to a non-renormalized theory of vacuum fluctuations or many other theories, you get the right order of magnitude for the cosmological constant. The question is, it remains, do we also get precisely this effect? And all I can say at this stage is that so you should watch this space and see what happens. And thank you very much.
All right, thank you, Ulf. Do we have any questions? While people are thinking of questions, I have just one. Maybe it's just my own ignorance, but so in the usual Casimir case, you have the two plates, and you move them, and you take a difference to sort of understand the force.
Yes.
What's actually moving in the time direction that you're taking differences of? Like I think maybe I just missed it.
So this is this picture. So the standard Casimir force, you have, let's say, in the simplest case, two mirrors, and these mirrors are interacting with each other via vacuum fluctuations. And you could also say these are two pieces of material. So like you take a piece of glass, that's one mirror, and another piece of glass, that's the other mirror. So you have an refractive index that has a profile that changes in space. So outside of the first mirror, it's the refractive index is 1. Then you hit 1.45 glass for the mirror. Then it's 1 in between. Then the other piece is 1.45, and then it's 1 again. So your refractive index changes as a step function. This is the picture for the standard Casimir forces. And then you get a force or a stress that is, or the force density is then localized at the surfaces. So you get at the inner surfaces, you get a force, and that this force density then moves the two dielectric objects towards each other. And in cosmology, you have a refractive index that changes in time, not in space. And that's all. That's the only difference. So the only difference from the beginning down, the theory of how to understand those Casimir forces is more subtle. So you need to worry about cosmological horizons, you need to worry about causality, but from the outset, the basic similarity is very simple. So you replace a variation in space by a variation in time. There's nothing more.
I see. So thank you. We have a question
What
from we have a question from Ted. Ted, would you go ahead?
Okay, thank you. Hi, Ulf.
Hi.
So I have a question about the very end proposal that the tension and the value of the Hubble constant might be addressed by this theory.
Yes.
My understanding was that that tension is between values inferred from the cosmic microwave background and values inferred from, say, redshift of 2 or less.
No. The tension, the main tension is so it's values inferred from the CMB and measurement of the Hubble constant right now. So at redshift 0.
Well, you can't measure it right now because it's a measurement of how things have changed. So you're
Yes,
measuring it from the supernova, for example, right?
No. It's not with supernovas. So it's this is done with so these measurements here, they are on the Magellan cloud, and so this is the little galaxy that is around our galaxy. So it's not far away, and but it's far away enough such that things move, and it's simply an application of Hubble's law. So the redshift,
hold on, in the interest of time, let me stop you because because this distinction isn't important for the point of my question.
Okay, so yeah.
So the point of my question is just that at the time of the CMB, as I understand it, the cosmological constant was completely irrelevant to the dynamics of the universe, and it's
Absolutely, yes.
Yeah, only at a redshift of 10 or something, maybe it started being important. So
yes.
I just don't understand how your theory could potentially address this tension between the value of the cosmological constant at the CMB time and, let's say, recently.
Completely clear. So very easy to answer this question. So you're right. The dynamics that led to the cosmic microwave background doesn't care anything about the cosmological constant. This is completely irrelevant. But then, so what you get is in this dynamics is you get fluctuations or correlations as a function of wave number. And now this then the CMB expanded and wave number gets translated into angular distance. So the way how you see those wave numbers, and that of course depends then on the evolution that comes afterwards. And in fact, the scale of the CMB spectrum is set directly by the cosmological, by the conformal time from the formation of the CMB until now. So the time it would have taken for light had there not been any expansion of the universe. So the standard time, this is the time that enters that scaling factor. And this is the only parameter in the CMB that actually depends on the value of lambda. So the people from that community, they are very adamant in defending their model and saying that we are proving the constant lambda cold dark matter model. And whereas in reality, it's just one parameter of the entire CMB measurements that depends on lambda. And this is the scale, and the scale is given by the expansion of the initial fluctuations until the angular momentum that we see now.
Okay, I think we
I
need
understand.
to.
Thanks.
Okay, I think we need to wrap it up there. Sorry, Steve.